I hope you've had a chance to see my video on the energy mass equivalence principle, and I'll just summarize it for you here if you haven't seen it yet. I want to point out that this equation right here actually uses real mass or relativistic mass, not m naught. M naught, not m naught, because m naught was what you studied like before you saw this equation, before you saw relativity. So I'm talking about m real, and I'm going to say that m real, or the relativistic mass, is m naught times gamma. Remember, gamma's got these properties where like gamma is the smallest it can be is 1, and the greatest it can be is infinity. Gamma can only be infinity if the thing that you're talking about is actually going the speed of light. So let's look at this right here. This energy then must be, well, this is the energy of a particle going a certain speed, and that means then that it's the rest mass of the particle times gamma, remember that's what our mass is right there, times c squared. So what I'm saying is that gamma, oh my goodness, gamma is 1 over the square root of 1 minus v squared over c squared, or 1 minus beta squared. So I want to point out to you that we're talking about dividing m naught and c squared by this scroot business right here. So we can get energy to be very big if you're moving very quickly. So I want to point out something also called rest energy. This is full energy, but rest energy is over here. Rest energy would be E naught, which is m naught times c squared. This is really the deal breaker, ladies. This sucker right here says that when things are just sitting still, they have a fundamental energy to them. And I guess what I mean is that, here's what I mean. What do I mean? I guess what I mean is that if you could eliminate the mass of a thing or annihilate something, if you could annihilate a thing, you could liberate this rest energy from the thing. If a thing ceased to exist, it would free up energy in the universe. So that raises the ultimate question, why does stuff exist? But I don't want to go into that right now. I want to say that annihilating things is a little bit tricky. You can get an electron right here, and if it is zooming that direction, and there's a positron over here, that's an anti-electron, if those two guys bump into each other, then they will annihilate. The mass of the electron and the mass of the positron cease to exist, and then the energy that was that mass is completely released. Although we would probably talk about this energy if those guys are zooming towards each other. But what if they were just going very slowly and they happened to bump into each other? They would annihilate. This happens in people's brains. In fact, there are scans called PET scans in which you can sit on a bench and they will pump you through of a radioactive material that it releases positrons sometimes, and guess what? Inside your head there are a whole bunch of electrons, and those electrons will be annihilated by the positrons. Now, how are you going to go up to a doctor and say, "Dear doctor, ma'am, would you please put something in me that annihilates bits of my brain so that you can look at the light that comes out of that"? I don't know, maybe you don't want a PET scan. Maybe you should get a PET scan. I don't know. At any rate, you should definitely see a doctor. Check this out. I'm saying next that the energy contained in a standard apple, I'm a Red Delicious kind of guy if you guys are thinking about me at this time. If you have a Red Delicious apple right there, and that sucker has to be, let's say that its rest mass is 0.12 kilograms. I want to figure out just how much energy we're talking about. The rest mass of a standard apple, here, let's shade it in a little bit. Look at that, that's art. Now, the rest energy of this apple is the mass of the apple times c squared. Now, c is the speed of light, and I'm planning to score it. It was already 3 times 10 to the 8th, and now it's going to get really, really big. The beautiful thing about the rest energy, well, I mean, it's in SI units, right? I'm going to use kilograms and meters per second squared. I'm going to find the energy to be 1.1 times 10 to the 16th kilogram meters squared per second squared. That's a joule. 1.1 times 10 to the 16th joules. Oh, ding! That's enough energy to power all of the United States energy needs for a half an hour. Holy cow! All you have to do is annihilate an apple. Now, let's hope that the US government has a whole bunch of anti-apples sitting somewhere, and they could use that to generate energy, or a bomb. Let's hope that they don't have that antimatter bomb, because that would be really unpleasant. But wait, isn't that what a nuclear bomb is? We're talking about fission, which is where you're breaking a stuff apart. Fission, you're breaking things into smaller pieces. Or fusion, which is you're bringing two pieces together. At any rate, if you do fission or fusion, if there are these nuclear reactions going on, you can liberate the energy of mass. You're making less mass exist than it did before. And of course, there's even annihilation, which is sort of not exactly either one of those categories. The beautiful thing about fission and fusion is it's a tiny, tiny fraction. The mass that is annihilated is a tiny fraction of the overall mass. But this is not a lecture on nuclear physics, so we're not going to talk about that right now. But note that if I had an apple and I could annihilate it very slowly over a very long time, I would get enough energy to light a 100-watt light bulb for 10 million years. Wow. Store your apples, they might come in useful. Oh, wait, that means the nuclear energy contained in this apple is way, way, way more than the chemical potential energy stored in this apple. Because if I eat this apple, I'm going to get what? You think an apple is 60 calories or 100 calories or something like that? That is, oh man, we're going to go to kilocalories, 100 kilocalories, and that's 4,186 joules per kilocalorie. Okay, so that's a lot of joules, but it's still only something like 400,000 joules, and this is something like 1, 1, and then 15 zeros following it. Here's some more zeros. There you go. That's a lot more joules. Dang. Okay, so here's where we're going next. I talked to you about rest energy, and I talked to you about total energy, and I'm going to say that total energy is rest energy plus kinetic energy. I hope that doesn't bother anybody. That's sort of the definition of what energy is. If I have a toaster flying through space, it has rest energy because it exists, and it has kinetic energy because it's moving. So I can solve this for kinetic energy, and I find kinetic energy to be total energy minus rest energy. We've got equations for each of these. What did Einstein say? E is mc squared or something like that, and he plugs it in here, and he plugs it in there. And I'm going to expand this just a little bit. This looks like mc squared minus m naught times c squared. Ooh, and mc squared is gamma times m naught times c squared, and then I'm supposed to subtract m naught times c squared, factor out the m naught c squared, and I get gamma minus 1. Oh, cool. Times m naught c squared. And that is the rest energy. So I'm saying kinetic energy is gamma minus 1 times rest energy. Interesting. And remember our gamma. Gamma is so important to play around with. You need to know how this function works at various speeds. So please, practice, practice, practice. Lots of gammas. Get a feel for gamma. I like to say that gamma of v equals 0.87c is, well, it's 2, right? Okay, and I also like to say that a gamma of 14% the speed of light is 1.01. So you get a feel for gamma. It gets really, really awesome when velocity gets really, really close to the speed of light. Gamma's like 1, 1, 1, 1, 1, and then suddenly, woo! Okay, that might be exaggerated. But here's another thing that we can do with kinetic energy. I just had written down that kinetic energy is, well, remember it's this 1 over 1 minus v squared over c squared, and the whole thing's supposed to be screwed, and that's times m naught, wow, m naught times c squared, and then I'm supposed to subtract m naught times c squared, because this is rest energy. This is gamma times rest energy minus rest energy itself. I can expand this by the binomial expansion because, see, as a scientist, I don't like a denominator with a radical in it. I think that's gross. You know what I like? Polynomials. Polynomial party. And you're invited. Come with me on this polynomial party. Here, no, I'm sick of brown. Let's do blue. Blue, 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 blue. I'm gonna factor out an m naught times c square, and I'm gonna expand this denominator right here by the binomial expansion. And I get 1 plus 1/2 v squared over c squared. See, that's my variable down here in the denominator. And I'm assuming that it's reasonably small. This would break down for high speeds. Then I add 3/8 times v to the 4th divided by c to the 4th, and I could go on, but I don't really feel like it because at low speeds, oh wait, that's just this term right here. Then I have to subtract m naught times c squared. Notice I've got m naught times c squared, and I've got m naught times c squared. So at low speeds, we get that the kinetic energy is approximately m naught times c squared times 1 plus 1/2 v squared over c squared minus m naught times c squared. And if you're clever, you may notice that this is m naught times c squared times 1, and this is negative m naught times c squared times 1, so this cancels that. And we can just combine this stuff right here, and watch with me as I do. I will cancel out a c squared, because there's one in the denominator right there, and I get kinetic energy is approximately equal to, wait a second, drum roll please, kinetic energy is approximately equal to 1/2 times rest energy times v squared. What? We knew that already! Yay! So let's make a graph. One final graph of kinetic energy as a function of speed, and of course beta is, this is the definition of beta, v over c. And I'm gonna get up to 1, and I'm gonna find that kinetic energy, let's do the classical one first. What do we have with classical? I think classical was supposed to be red for blood, yeah. So classical kinetic energy comes out here and it's 0 at 0 speed. That's fine. And it's quadratic. It's a lovely parabola, right? That's nice. Now, quantum why do I keep saying that? I'm so sorry. We are talking about relativity. Relativity corrects the kinetic energy equation by gamma. So it prevents it from ever hitting the, prevents it from ever hitting the speed of light. So I'm gonna have very similar performance. Remember, we said at low speeds, kinetic energy is 1/2 v squared. So this is still a quadratic at low speeds, but at some point, probably here about 14%, it's going to substantially deviate, and then we get this performance right here. This is relativistic kinetic energy, and this sucker right here is classical kinetic energy. And the deviation is this term right here, and those terms right there. That gives you a view of your error. So expanding functions and looking at when they begin to have significant error is a really cool physics step. I'll give you a smiley face right there. That's a freaky smiley face. I'll give you a better one. There, and an exclamation point. Goodbye. M naught, not M naught, because M naught was what you studied like before you saw this equation, before you saw relativity. So I'm talking about M real, and I'm gonna say that M real, or the relativistic mass, is m naught times gamma. Remember, gamma's got these properties where like gamma is, the smallest it can be is 1, and the greatest it can be is infinity. I hope you've had a chance to see my video on the energy mass equivalence principle, and I'll just summarize it for you here if you haven't seen it yet. I want to point out that this equation right here actually uses real mass or relativistic mass, not m naught. Saying is that gamma, oh my goodness, gamma is 1 over the square root of 1 minus v squared over c squared, or 1 minus beta squared. So I want to point out to you that we're talking about dividing m naught and c squared by this scroot business right here. So we can get energy to be very big if your gamma can only be infinity if the thing that you're talking about is actually going the speed of light. So let's look at this right here. This energy then must be, well, this is the energy of a particle going a certain speed, and that means then that it's the rest mass of the particle times gamma, remember that's what our mass is right there, times c squared. So what I'm moving very quickly. So I want to point out something also called rest energy. This is full energy, but rest energy is over here. Rest energy would be E naught, which is m naught times c squared. This is really the deal breaker, ladies. This sucker right here says that when things are just sitting still, they have a fundamental